Hello, good day from here. Thank you for stopping by my channel. Thank you for watching this video. In this video, I will be talking briefly to linear models in Stata. I'll talk to, to predictive analysis, linear regression models, and hierarchical regression. My name is Peter Daniel. I have a PhD in applied economics and also a lead consultant in Smart Africa R&D Consult. So in this course, I will run you through the slides and talk theoretically on the various models, after which I will do a hands-on session to operationalize all I'll be teaching using Stata. All right. Introduction to predictive analysis. So predictive analysis refers to using statistical, historical data, machine learning, and artificial intelligence to predict what will happen in the future. In this kind of analysis, you are making use of what is currently known to determine what is unknown, or to rather predict what is unknown. If I try to compare predictive analysis and prescriptive analysis, I say predictive analysis gives an indication of what may happen. It's prescriptive analysis. Why prescriptive analysis shows the way to make it happen, that is regression. And prescriptive analysis differ in that it not only identifies what's likely to happen, it also presents the user with specific options. That's when we talk about optimization model. That's the linear programming model. So types of predictive analysis, we have regression analysis, logistic analysis, probit analysis, multinomial logic analysis, ordered logic or ordered probit, Tobit analysis, and hierarchical regression. These are the various kinds of regression analysis that are predictive in its operations. So for this video, I will talk extensively to regression analysis and logic analysis. Then I'll try to do the hands-on session on regression analysis. Now, regression analysis can be has about 4 different types. We have the linear regression. Now, the linear regression, in this kind of regression, both the dependent and the independent variable are in its natural state. The both dependent and the independent variable are discrete variables. They are just random variables. They are the raw data, as it were, when you collect it. We also have the log linear regression analysis. Now, the log linear regression, The log linear regression, this kind of regression where you also call semi-log, better still, call semi-log. So semi-log now having 2 types. So that is log linear or linear log. All right. So if it's log linear, it means that you will log your dependent variable while you leave the independent variable in its natural state as raw data collected. But if it's linear log, it means the dependent variable is not log while the independent variables are log. Then we have the Cobb-Douglas regression. The Cobb-Douglas regression means you will log both the dependent and the independent variable. Tobit model, which both doubles as a maximum likelihood model and also a linear model, although the result comes out more often as an OLS model, is a censored regression. What this means is that you have the ability to left censor, right censor, or probably you censor in the middle. What this means is that when you have a dependent variable and probably you want to do analysis with only a particular portion of the data set of the random variable, Tobit model gives you the ability to censor your data. So when you run a regression model, the output comes up like this. Just as soon as I finish the slides now, I'll quickly go through and do a hands-on session using Stata. Now, one of the problems a lot of people face is what does the result I'm having, what does it mean? How do I interpret it? So the output comes out like this in 3 tables in Stata. The first table is the ANOVA table. Then we have the summary table. Then we now have the other table, that's the table that has the coefficients. So what are the key things you look at here? You look at your F statistics, you look at your R squared, then on the tables you look at the T values of the coefficient to determine T or P values, whichever one works fine for you, to determine which of the variable is significant and which is not significant. When you run a regression model, an F value that is above 5 is acceptable. It's acceptable. It's good that your F value is above the figure of 5. In this model now, the F value is 6.3. So, and you see the P value is significant at 1%. Also, when you run a regression model, an R square that is above 50 is desirable. Now, it's not in all regression model you are trying to look for a high R square. A lot of students try to disturb themselves about having a high R square. It's not all the time. Sometimes you run a regression model to look at variables that are significant, not necessarily to check if the R square is high. Or however, the rule of thumb is the R square should be at least above 50%. In the case of this result on the screen now, the R square is way below 50% and not desirable in model. It's not you should rerun this model, trying other variables to see that you get a good R square. But the P value, the F value shows that the model itself was well specified. But in interpretation, it shows that the model was well specified. While the R square shows the extent of variation in the dependent variable that is as a result of the independent variable. For example, in the regression on the screen, if I'm trying to interpret R squared, I will say that 9% of the variation in the dependent variable is as a result of the variables captured in the model, while the remaining 91% will be attributed to error. Now you understand why we say the R square should be above 50. If you specify a model and you are giving a larger portion to error, then what is the use of the model? So that's what that talks to. Then another key thing you want to interpret is your T value. And your T value, based on the level of significance that you are testing your coefficient, normally this T value are tested in three different coefficients: at 10%, at 5%, and also at 1%. It is significant at 10% when the T value is 1.68, and above, but below 1.95. It is significant at 5% when your t-value is 1.95, above or below 2.58. It is significant at 1% when your t-value is above 2.58. Another thing you look at as well is to ensure that to look at the signs of your coefficient. The signs of your coefficient will also determine the story you will tell around the data. The coefficient that are positive, coefficient means there's a direct and proportional relationship between the independent variable and that particular the dependent variable and that particular independent variable. While the negative coefficient depicts an inverse relationship between the dependent variable and the independent variable. If I talk to this table now, we see, mind you, you don't interpret the coefficient that is not significant. Any coefficient that is not significant, you ignore it. So coming down to the result we have on the screen, we see income is significant at 1%. We see food consumption is significant at 1%. We see occupation is significant at 5%. And the dependent variable here is BMI, this body mass index. Now this was the training slides I used to train people in the health sector. When I'll be doing the hands-on section, I will generate other hypothetical data. The data I used here too was just generated randomly. For the training session, I also generate, for the practical session I'll be doing on data, I'll just generate a random variable. The essence of my video is that you understand what to do, the right thing to do, and not to cram the approach. So that you don't bother yourself trying to get the same result. What is important is that you know the right thing to do, that you control the data and know, okay, this is what it should give me, because you know it, the data does not forge, does not make you to be disturbed based on the result. Okay, so if I'm going to talk to this now, the income now, we see income here is significant at 1%. The coefficient is positive, has a positive sign, and the t-value is significant at 1%. So if I'm to interpret this, I will say that a unit increase in income of either the respondent will lead to about 1.2 unit increase in the body mass index of the respondent. So unit increase in the coefficient in the income will lead to 1.2 unit increase in the body mass index. This is a regression output of a linear model. When you interpret a linear model, you interpret unit increase leads to unit increase. When you interpret a semi-log model, you interpret percentage increase lead to unit increase, or unit increase lead to percentage increase, depends on where you log. Then when you interpret a Cobb-Douglas model, you say unit percentage increase lead to percentage increase. So you look at, if you pay attention to my wordings, I said that unit increase in the income of the respondent will lead to 1.2 unit increase in the body mass index of the respondent. This is a case of a linear model. All right. So for a Cobb-Douglas model, is also a result of the Cobb-Douglas model. So if you look at the codes, you see we have the log. We have introduced the component of the log. Introduce the component of the log in this model. So when you check here, income is also significant here at 1%. We have food consumption is significant at 1% as well. If I'm to interpret the food consumption, I'll say that a percentage increase in food consumption will lead to about 7.7% increase in the body mass index. Now pay attention to my language. I'm now saying the percentage increase will lead to percentage increase, and of course my F value is above 5, which is okay, although the R square is low, but based on the F value, this model can be accepted. All right, so let me go to the next slide. All right, okay, so Cook Douglas now. So let me go to the next slide now. For a Torbit model, like I said, when you want to run a Torbit model, you have the ability to censor, either you censor leftward or you censor rightward. Torbit model is appropriate or is best fit when you have a dependent variable that is continuous. When your dependent variable is continuous, it means your dependent variable assume figure between 0.1 up to maybe the maximum you may have, point something. So if you have this kind of dependent variable and probably you want to run a regression with 1 point above, you want to neglect the zero, the worst dependent variable below 0, you can censor. And if the otherwise you want to run regression with a model, the dependent variable below 1, Torbit model is the best approach. In the field of applied economics, field of agriculture, Torbit model is best suited when you want to run uh, any analysis where productivity is your dependent variable. Sometimes Torbit model are also used when you want to run a dependent, when your dependent variable is food security, and that is if you've captured your food security in continuous way, although it's usually not the best, but sometimes can be adopted. So now Torbit model, because the essence of Torbit model is not necessarily to look at the R square, because Torbit model does not give you R square, it gives you a pseudo R. So you pay more attention to the chi-square in this case. Now in this case, there's no F value. The chi-square is what you pay attention to. And your chi-square is expected to be significant. So based on the result we have on the board, this model has to be rejected because the chi-square is not significant. Your chi-square should be significant at worst case at 10%. Remember, I told you that this data set which was generated hypothetically just to teach the student, the participant, on how to operationalize the model, not necessarily to get a good result. So in this case, the chi-square the model as a overall will be rejected because the chi-square is not significant. The chi-square in Torbit model tells you if the model was well specified. Okay, but if I'm to go through the t-value, you see none of the values, none of these coefficients, none of the variables, is significant. All right, next slide. I hope the data set I will generate will be able to get a significant model so I can interpret properly. So hierarchical regression is a technique which can be used to compare several different linear models. The basic idea is that we first fit a linear model, regression model, with just one explanatory variable. Then we fit another regression model with additional explanatory variable. If the R square, the proportion of variance in the response variable that can be explained on the explanatory variable in the second model is significantly higher than the R square in the previous model, this means the second model is better. This is actually also called a stepwise regression. This is a kind of regression you run when you are trying to get the best model possible from your different data set. It's called stepwise because you have your dependent variable constant while you keep alternating the independent variable. That is, you put the first one based on the R square. That will be what you use to judge the uh, the 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 effectiveness or the quality of the model now. So when I'm doing hands-on, I will show you how that can be done. We then repeat the process, fitting additional regression models with more explanation and seeing if the newer models offer improvement over the previous. So What this means is that I have my dependent variable, right? I put the first independent variable, I repeat the same process with another independent variable. If that new variable I added improves the R square, then it's good for the model. If otherwise, then I'll remove it and try another one. Now this is how the regression output comes out. It's just like your normal OLS. Alright. Okay, this is model 1 now. You see in model 1, I only have food consumption. Now in model 2, I've added height, right? Now in model 3, I've added age. That's how are you, right? So that's how it is done. Then of course, this slide is just a brief interpretation of the regression model. All right, thank you. So I will quickly go to hands-on now. Then once I finish this, I will see if I can also, based on what, once I finish this, I will quickly talk to Logit's model in this video as well, so we'll have a full video. All right, so in my previous video, of course, I've showed you how to launch your stata, bring your variables down there, and also let's briefly examine the variables. So the variables, these variables, I think, okay, this is for a catfish production enterprise. So we have the input, which is fingerlings, feeds, labor, drugs, the fuel used, the size of the pond, and I think I will just drop fuel. Drop fuel. Let me also drop fuel here, so that all right. So let me talk to production, core production variables. All right. So we have the data and the logged one, the data as collected from the field and the logged data. This is now logged. So I have 3y here. This is my first dependent variable output. It's not logged. I have the one that is logged. Then I added another y, which is for the Tobit model analysis. All right. So first thing to do is to, okay, let me clear this result window. Yeah, clear result window. So on your stata, the first thing to do is to set your working directory. So I say cd, I want to work from project files. No, I want to work from stata training. So I will come and I'll copy the path. I'll copy as path. Copy as path. So I've set my working directory. Now I want to set more off. I don't want to be seen more. I want all my results to display at once. Then what else do I do next? Okay, I want to log using let me log using regression training. Regression underscore training. All right. So I've logged using regression underscore training. So the first thing is, of course, you describe. Let's see the kind of data, how it is stored, what it looks like. So I've described all my variables. I've seen the storage type. As it displayed, then I see the variable label. So we see now that label does not have a label, and I want to label. So let me say label define, and to label, okay, label variable, and to label variable label, let me label it label as well. Okay, and I also want to label variable natural log of label. Let me label it natural log of label. So let me describe again so you see the changes. So now all the variables are now labeled. Now the value label is, I've not given at since it's just a regression model, there's no need to give it a value label, and more so I don't have categorical variables, so there's no need to label that. All right, so the next thing is I want to summarize. So I have summarized, I've seen, just to confirm if my observations are complete. So I have 205 observations and they are all complete. None is missing here. And I have the mean, the standard deviation, minimum, and the maximum. All right. I hope you're enjoying this video. Please do like the video and subscribe to the channel. I'll be doing a whole lot of analysis on Stata this period. I'll be talking to a lot of regression models, a lot of profit models. I'll be talking to food security poverty analysis. I'll be talking to propensity score matching. I'll talk a lot about. You stand to gain a lot when you subscribe. I will drop a lot of videos, and I would like you to benefit from what I will be dropping. Feel free to reach out to me via email, my phone number. You can always check out my website www.smartdreams.com and ask any question you have. I'll be glad to respond and support your analysis career. And also, if you have a project you are running and you need to know the best approach or methodology to adopt, feel free to reach out. Kindly subscribe and help us promote the channel and reach out to other people so that they come and get a very good knowledge. All right, so let me do the first. I'll take it based on the slides now. I will go to the regression models. So linear model. So let me do the linear model. So to run a linear model, I will just say regress. So if my dependent variable here is output, then my independent variable is fingerling, speed, label drug, font size. So I do this, then enter. All right. So like I told you earlier, the result comes out with 3 tables: ANOVA table, the summary statistics here, and of course the coefficient table. Wow, this is a very good analysis as it is. So I said earlier, we look at the summary statistics. The number of observations is 205. All right, I'm timing myself. I don't want the videos to be too long. Now, the F value is super high, 597. No wonder we have a very high R square of 93%. Now, this is hypothetical for the purpose of this analysis. All right. So to interpret this, I will say the F value is significant at 1%, and it does shows that the model was well specified. Then the next very summary statistics I look at is the R square. The R square of the analysis is 93.75%, which shows that, which suggests that 93.75% of the variation in the dependent variable, which is output now, which catfish output, is as a result of the independent variable, which are the inputs now, which are the inputs. Why the remaining, I think we have about 6.25% that is remaining before it gets to 100 now. If I'm correct, you just minus that figure from 1 or minus it from 100. Let me quickly do that. So you see what I'm saying. Calculator. So to calculate the error term, you just minus 1 minus 0.9375. Yeah, that will be 6.25. I multiply, of course, by 100. Yeah, 6.25. I was correct. So 6.25% is as a result of variables not captured in the model, which is now the error time. All right. Now, talking to the coefficient output. Now, the t-value for fingerlings is significant at 1%. For feed is significant at 1%. For labor, it is significant at 1%. For drugs, it is significant at 5%. For pond size, it is not significant at all. All right, so let me interpret this. Usually, the production models, they are always expected to, you always want to have a positive a priori expectation, most especially when it's Cook-Douglas, although this is in a linear form, but it's not always so in practice. So to interpret this, I'll say a unit increase for fingerlings. Fingerlings was positive, has a positive coefficient, and statistically significant at 1% probability level. This and suggests that a unit increase in fingerlings will lead to 0.68 unit increase in catfish output. Right? Excuse me. Also, a unit increase in feed, feed is also positive. So unit increase in feed is positive and statistically significant at 1%. So unit increase in feed will lead to 3.8 unit increase in the output of catfish. So let me talk to drugs. Drugs is positive and statistically significant at 5% probability level. It shows that a unit increase in drugs will lead to 0.009 unit increase in the output of catfish. So that is just all about a linear regression model. So we now have semi-log, which can either be log linear regression or linear log. Remember, I said the log linear means that the dependent variable is logged while the independent variables are not logged. So let me log this. I'll say so to be regress, the log output, this is log, then the independent variables are not logged. Yeah. All right. So so this is a log linear. Dependent variable is log, the independent variable not log. So you see, what are the changes? The F value reduced, the R square increased. No, sorry, the F value increased, concurrently with the R square, and okay, now drugs became insignificant, and of course labor size became insignificant. Okay, drugs became, and pawn size became insignificant, but fingerlings, fees, and labor still remain significant, although the T value increased. All right. So now if I'm to interpret this, let me interpret uh, feed, for instance. I'll say a unit increase in feed will lead to 0.16% increase in the fingerling output. So to get that, all we just need to do is to say you multiply the coefficient by 100 to get the percentage increase. So I'll say 0.001622 multiplied by 100. Okay, so that's that. So a unit increase in the feed, that is, if you give the catfish more feed, it will lead to 0.16% increase in the output of catfish. The coefficient is positive as well. That's why we have a proportional relationship. Unit increase leading to unit increase. Unit increase leading to percentage increase. All right. Okay, I believe you understand. I hope I'm not too fast, and I'm trying to take it step-wise and slowly so that you have an understanding, so that you can do your analysis yourself and better understand your regression models. All right. We can also repeat the same process now, but now the dependent variable is not logged, which this is now linear log. So I will put output is not logged, then the independent variables are now logged. So that's linear log. There's also semi-log. Okay, so in this case, the F value reduced, the R value also reduced, and just a slight change in the significance of the coefficient. We see now that the coefficients are higher, very high. You can't obviously interpret this because the coefficients are just too high. Of course, it may just be a problem with the data set. Again, the T values, drugs became significant now. So you follow the same way like I interpreted the first one to interpret this. So, but in this case now, let me just take an example of drugs now. I will now say a unit increase, a 1% increase in drugs will lead to 134 unit increase in output. So it's now percentage increase leading to unit increase. You see the difference in my terminology. All right, I believe we are making progress. All right, so let's come to the most popular one, which is the Cobb-Douglas or double log regression model. I think I have a video that talked to Cobb-Douglas regression alone. You can leave that out. So in this video now, in this analysis now, I beg your pardon, we are now doing the logged dependent variable and logged independent variable. So they are both logged. So in this case, let me say, so I'll say regress, the same process. So now I'm regressing the logged output and the logged independent variable. Alright, enter. Wow. The R square is super high. No, the R square is high, the F value is high, then the coefficients are now very moderate. Usually, the Cobb-Douglas is the best approach to pick when best regression when you are doing a production function, or most often the most preferred amongst the 3 or 4 kinds of linear regression. And the reason is because it you can how do I explain to you now? It helps to reduce the value of the coefficient. It can be twice differentiated, and yes, I think that's two major reasons. It can be twice differentiated, and it helps to, of course, reduce the value of your coefficient. It helps close the gap. Okay, it also helps if it helps reduce the variation among variables that you are using in the analysis. Just if the standard deviation is wide or high, when you adopt the Cobb-Douglas regression, it helps close the gap between the standard deviation and the mean deviation, as it were. So in this case, we're interpreting percentage increase lead to percentage increase. Drugs now is not significant. Font size is as well not significant. But fingerlings, feed, and labor still remain significant. So if I'm to interpret this, let me interpret, and Cobb-Douglas regression is always expected to be concave. In this case, it is concave, which is okay. But there are cases where it's not concave. Concave meaning that all the coefficients will be positive, all the variables should have a positive coefficient. But this may not be the case in all times. So if you have a Cobb-Douglas regression that you don't have all positive, you should not worry yourself. You cannot as well interpret that way once other parameters are well specified, and of course having a good value. So the F value is 781, significant at 1%, which shows that the model was well specified. The R square is 95%, which suggests that 95% in the variation in catfish output was due to the input or due to the variables captured in the model, while the remaining 4.85% is as a result of variables not captured. That should be 1 minus 0.58, 0.515 to get the error term. So that will be as a result of variables not captured. These are the error term. Now the t value, if I'm to let me talk to feed. The variable feed has a positive coefficient and is statistically significant at 1%, and suggests that a percentage increase in quantity of feed given to the catfish will lead to about 20.23% increase in the output of catfish. The same approach goes for the other you want to interpret for fingerlings and label. Alright, quickly let me talk to top bit regression analysis. Now you can do top bit regression analysis now if I don't want this video to be too long, it's already getting long. If you want to censor your dependent, so where does it apply? Let's say you have done your analysis and you have output which can also be called yield. But however, you want to check productivity. Now productivity is a function of your output ratio of the output to the input, physical term now. And most time productivity, whether a farmer is sub-productive, productive or super productive, and it's always a continuous variable. We say a farmer that has 1 point above is productive, while those below 1 point are not productive. So you might want to check factors that affect productivity or factors that affect in, that makes them not to be productive as such. So to do that, you have to get that ratio statistics, which will be the total output all over the total input in physical units. Now that most often it will come out in this form, in form of a continuous variable. Let me summarize that so you see. Summarize topics. All right. So you see that the minimum is 0.9 and of course the maximum is 1.4. So you run the series a continuous variable. Now Tobit is in between OLS. What we've been doing is ordinary least square regression technique and maximum likelihood estimation technique. Now the OLS regression, the maximum likelihood regression has the ability for you to check the marginal effect. But Tobit will not give you marginal effect that is different from the normal coefficient, that is why we say it's more or less an OLS regression. But it differs in the sense that it does not give you an F value. In the place of F value, it gives you a chi-square, like a maximum likelihood. Some people make mistake of trying to still check for marginal effect of a Tobit model. There's no need, because it's just going to be the same with your coefficient. So to run that, I'll come to statistics. I think I've been using command. Let me use the menu now. So you just come to statistics, come to linear regression, come to sensor regression, you see Tobit. So you click Tobit. Once you click on Tobit, it gives you what do you want to be your dependent variable. So I will come, I have y Tobit. I saved it y Tobit. Now the independent variable, I come, I can pick, I want to use the logged ones. So let me pick the ones I logged. Just by clicking on it, it will automatically come up. So it drops. Yes. So it's asking what kind of sensoring do I want. So is it left, no sensoring at the left, or right sensoring? So let me do no left sensoring. Let's sensor at the right sensoring. So let's say let the value be 1. Okay, let me specify it. Let it be 1 as a cutoff point. I'll submit. So okay. So I'm saying each to bit should be done. When I say right, I'm saying the analysis should be done with variables that are equal to or above 1. You can see it here. Right censored variables that are equal to or above 1. That's what I have just done. Of course, these are chi-square. Right? So the analysis variables equal and above 1. So let me do left censoring too, so that I'll now talk to all the interpretation at once. No right censoring. Let me specify the left censoring 1 as well. So you see that now. Variables that are below or equal to 1. Okay, let me do the last one, then I will now talk to the analysis. We can censor both places. So let's say, let's use the medium now. Let me see. Okay, we have 0. So I can say let it censor 0.05 and 0.05 and 1. So let me work with that. No particular reason, but let's say we'll get a reason later. 0.5 and 1. So I'll just say okay. Okay, so this is okay now. Now let me get that now. Okay, so let me talk to, yes, what we have done here is to say, okay, do an analysis for me for dependent variable that are above or equal to 1. So this is actually the factors that affect productivity now. Which of these variables will make these farmers more productive? The chi-square is significant at 1%. We can see that already. Oh, my time is past, man. It's significant at 1%. We can see that already. I hope I've been able to communicate with you. I didn't want it to be too fast. I wanted to get this and get it well. Now the top bit now, we are saying now. So now let's pay attention to the t value and see which are significant. So in this case, I think only labor is significant. Labor and font size is significant. Font size has not been significant. Now you see now it's now significant and affecting productivity as well. And they have positive coefficient. So what this is saying is that now you interpret your Tobit model like the form of a linear model. Unit increase will lead to unit increase. So we see that in this one now, based on the result, a unit increase in labor will lead to about 0.018 unit increase in catfish output. Also, a unit increase in the pond size will lead to about 0.14 unit increase in the catfish output. All right, so this makes sense. So for the left censoring as well, okay, of course, we see, yeah, for the left censoring, we see that, of course, the chi-square is still significant. The pseudo R now is high. According to Gujarati, we say try and get a pseudo R that is above 34%. This is 56%. The pseudo R here is pretty low, but this is better here. But however, the pseudo R should not be interpreted in any time as an R square. It's a pseudo R. So this will now have, oh, thank God, finally I have a negative coefficient I can interpret here. So the other part is productivity. This is people below the 1. I don't think they are not productive in this case. But okay, let's just interpret as productivity. So we see pond size is negative, has a negative coefficient. So let me interpret this. I've been interpreting a positive coefficient. So this says that the pond size is statistically significant at 5%, has a negative coefficient, and it suggests that a unit increase in pond size will lead to about 0.9195 unit decrease in the output of catfish. Yes, I've been able to talk to negative coefficient now. The chi-square, to interpret the chi-square is 62.04, which is statistically significant at 1%, and suggests that the model was well specified. Okay, yes. Okay, so let me draw this session to a close. in the next video now, I will talk to other predictive models. I will deal with, I've been able to talk to OLS generally here, except topics that is the bridge of OLS and MLE. In the next video, I will talk extensively on maximum likelihood estimate. Thank you very much for watching this video. Thank you for your patience. I want to please ask you, please, to subscribe to my channel. Please refer your friends, your colleagues to my channel so that they learn the right thing to do and they are able to do the analysis themselves and tell a good story on the analysis. Before I draw a final curtain, there is a slide where I interpreted a regression analysis. Let me just read through it so you see. So from the result, the F statistics was 6.0. You can see it on the table, which is significant at 1% level of probability. This implies that the overall effect of the explanatory variable was statistically significant. The R square was 0.09. This implies that 9% of the variation in body mass index, that is dependent variable, was due to the explanatory variable captured in the model. The remaining 91% was due to other variables not captured in the model and the error term. So income, food consumption, and occupation had positive coefficient and were significant at 1%, 1%, and 5% probability level respectively. This implies that a unit increase in income, food consumption, and occupation will result to 1.2, 1.5, and 2.1 unit increase in body mass index of the respondent respectively. So this is how your interpretation should flow. You can use this as a sample to interpret all your analysis. Now, thank you very, very, very much for your patience and watching through. Please subscribe once again. Please subscribe. Thank you. And next week I'll be doing another video that will have all the maximum likelihood together that you can learn. Thank you very much. Hello, thank you for stopping by my channel. Thank you for watching this video. In this video, I'll be showing in simple steps how you can run a stochastic frontier production analysis using Stata. So what you can see on my screen currently is the Stata interface. So once you launch your Stata, this is the first interface you see. So first thing I want to do on my Stata is to set my working directory. So I'll use a simple command cd, then of course I'll go to where the file is, then I'll copy the file paths. So this is the file path. I'll copy as paths. So what I'm doing here is just to set my working directory. That is where anything I save, what I'll be doing is where everything is saved. So I've set my working directory. I want to set more off. The essence of this is to make sure that all my results are displayed at once, and to clear all, and just to set the refresh data memory. Then next now to do is to bring the data sets. I'll use the command use. I go back again and open the folder. This is the data set is currently saved in Stata file, so I'll copy as path as well. You go to the document, hold down the shift button, right click, and you copy as path. I come back and I paste it. So what that's it, the top far right, you can see it was empty before. Now I have the data set. Next thing I want to do is to log. I want to log using stochastic frontier production analysis. Yep. So enter. So that's what I'll be using to save my results. Then I want to take the summary statistics of all the data sets sum. So that will just show me. I just want to quickly check if all my variables have the same observation. So the first thing I will do now is to run
the first part of the model so that I can get my lambda. So I will say I'll use the command frontier. Frontier, so it's frontier. First thing, frontier, put your dependent variable, then the independent variables together. You just need this. Okay, frontier, dependent variable, then independent, and of course it have enter key. So I have it on my screen. I want to run that again so that you understand frontier. You just tap the dependent variable first, then of course followed by the independent variables. Enter. So that's that. So my lambda, you can see my lambda, which is the core, one of the major statistic of stochastic frontier production analysis. It must be more than 1. At the worst case 0.999, so we know it's approximately 1. Then of course my model is concave. I can see where all are positive coefficients. Alright, so I want to predict my TE, so I'll say predict. Let me call the variable TF TE. So predict a new variable TF, because that's technical efficiency. So when you look at this part, I don't have that variable. So once I click on enter now, a new variable is generated. So you see that that's a new variable. I want to take the summary of it. Summary, sum TE. So click on enter. So that is the summary. So you see, this is the main technical efficiency, and of course the minimum and maximum. Now I want to run the simultaneous model that has both the production function, the Cook-Douglas, and the inefficiency component. That is both the frontier, the first part of the model, and the second part of the model. So I'll say frontier. I'll just copy this command and paste. So what I have here now is, of course, frontier. By the first model I ran, is still the same thing to this one. This is what is now different. This is the inefficiency part of the model, and of course all the socioeconomic characteristics that was hypothesized to influence technical inefficiency or technical efficiency in your model. And I click on enter. And once I click on enter, you see the model as it runs successfully. So this is the first part of the model. We did that before, but now we don't have the lambda again. So that's the essence of running it the first time without having the inefficiency component. So now this is inefficient component. Of course, you look at the z values to pick the variables that are significant and insignificant. So that is the result. So the next thing I do is to close my log. So log close. So I've saved the result. Now that's just the simple steps to run stochastic frontier production analysis. Now thank you for watching this video. If the video was useful to you, kindly hit the like button and also subscribe to my channel for more important analytical process. Thank you.